Hello and welcome. In this video, we're going to solve for total current in the circuit using just a resistor value and the power dissipated across one resistor. And we're also going to use the values that we get from that, the total current, to solve for R2 value, the resistive load of R2. So to start this out, we kind of need to know what we're working with. So when we look at the circuit, we see that this is a series circuit. There's only one pathway for current. So we know that if we find IT, that's going to be the only current in the circuit, and it's going to be the current through R1 and the current through R2. Right now, we know very, very little about R2. We don't have its ohmic value. We don't know its voltage drop. We don't know its power, and we don't know the current through it. So we know nothing about R2 other than the fact that it's a part of a series circuit with R1. R1 we know more about, though. We know that it receives a 10-volt source and that it's going to have some kind of voltage drop. And we know that it has an ohmic value of 620 and that its power dissipated is 87.9 milliwatts. And we know that power is the voltage, and we see that right here. Our watt meter here is measuring voltage around the resistor on one probe line, and then the other one is measuring the current through the circuit. And so those two together is going to give us this power value. So we want to use that power and that resistor to determine the current through the circuit, and that current is going to give us some information about R2. So that is our goal. So let's pull out a couple of laws. Our power law, E-I-N-V, and then our Ohm's law, V-I-N-R. We know we can use both of these two laws together. We can combine them together to solve for other values. So we'll do that. We know that we were given power and that we were given resistance. And so we need to combine these two in a way that allows us to get IT as our final goal. So we'll say that our power, specifically the power they gave us, which is P1, it's the power dissipated across this first resistor, P1. And we know what that is equal to, but we also know the power law says that that is equal to our total current IT multiplied by the voltage R1, right? The voltage drop across that first resistor, not the total, right? Because that would give us total power. So we need to make sure we pair that together. We want to actually solve for IT, so we're going to keep IT in play here, and we're going to try and get rid of this voltage. We're going to try and get rid of this VR1 requirement. That goes back to our Ohm's law. Ohm's law says that if we know a resistor value, we want a voltage, we can circle voltage and say that that is current times resistance, specifically IT, since that's the only current in the circuit, multiplied by the resistor we want to know the voltage drop across, R1. We can combine those together and get a new power equation that says P1 is equal to IT times IT times R1. Right, we can combine those ITs together. That gives us P1 is equal to IT squared divided by R2, R1. All right, now we have one of these values. We know what R1 is, right? We don't know what IT is. We do know what P1 is, though, because we were given that. So now we just got to rearrange this so that we can solve for what we actually want. And so that's going to mean that we rearrange this by dividing R1 to both sides. R1, remember that equal sign allows us to do this. R1. So now we've got P1 divided by R1 equals IT squared. We'll rewrite that. We'll say P1 divided by R1 equal to IT squared. We want to get rid of that squared symbol, right? We don't want this squared up here. So to do that, we can mathematically take the square root of both sides. Right? That knocks this off and it gets rid of the square root on this side, so IT is all by itself, and it leaves P1 and R1 underneath the square root symbol. So we'll have a final equation here that says P1, it says IT. IT is equal to the square root of P1 divided by R1. Right? We can plug that in. We can solve for IT using this equation, and then we will know the current through the R2 resistor also, and that would be one value for R2. So the first prompt asks us to find the total current. So this is actually one of our goals. So let's start there. Say that we have the square root of the power that they gave us, which is in milliwatts. We got to watch out for that. It's 0.0879. That gives it out of the milliwatt range. We'll divide that by R1 value, which is 620. That gives us a really small current. That's what we wanted. So we'll say that our IT is equal to 0.0119. We'll move that decimal point over. We can say that this is the zero base location, so we can go 1, 2, 3 backwards, -3. Right, so now we have a final answer of IT is equal to 11.9 milliamps. So now that we know that that's the total current, IT, 11.9 milliamps, that's going to be the current through both of the two resistors. And so we now know something about R2. We know that that is the IT current. But we don't know what the voltage is. We don't know what the resistance is. That's what our goal is next, is to find the resistance of R2. So we need to figure out what R1 used in terms of voltage so that we can figure out what the voltage drop across R2 is. And that's actually using a law called KVL. KVL is Kirchhoff's voltage law, and it identifies the fact that if we have a voltage source, we can subtract the voltage drops that we know we lost, and we'll end up with the voltage that is left over, VR2. And that's what we're looking for. We're looking for VR2 here, so that we can compare it to what we know the current going through that resistor is, and then we'll be able to find the resistance of that resistor. So let's solve for that. We're going to say that we want to know voltage drop across R1. So we are aiming at VR1. And we'll set that equal to our Ohm's law. So we know voltage, current, and resistance. So VR1 is equal to IT, the only current in the circuit, multiplied by R1 resistor. Which means that we can find VR1 right now. We can plug that in out and say that we have IT, that's a small little milliamp value, 0.0119, and we will multiply that by our R1 value of 620. That's going to give us a voltage, right? That's the voltage drop across that R1 resistor. And so we'll set that equal to 7.378 volts. That is over here. That's this voltage drop. That's what this meter is reading right here to get this power value that they marked. So it has 7.378 volts. We can use KVL to subtract that. Now we know our voltage source is 10 volts and that our VR1 is 7.378 volts. And now we're going to get the leftover voltage across the next component. Do that here. So we started with 10 volts. We lost 7.378 volts. We're left with 2.622. So VR2 equal to 2.622 volts. Immediately, look at that and say, well, the first one consumed more voltage than the second one, so we expect R2 to be smaller than the first resistor. It has to be less than 620 because it used a substantially less amount of voltage. Okay, that gives us two things, right? Now we know the current through R2 and we know the resistant or the value of R2 in terms of voltage. So we can use our Ohm's law one more time. Say that since we want to know resistance, we can say that's voltage over current. So R, specifically R2, equal to voltage over current. We know only one current, so that's got to be IT, but we also know that this is going to be R2's voltage so that we match R2 with the voltage that it has. Okay, so now we can figure out the resistance of R2. Set this out here and say that we know VR2 is 2.622 volts divided by our total current. Total current is 11.9 milliamps. Watch out for this. When you have the milliamps on the bottom, you really need to account for those zeros. Let's send this out. So 2.622 divided by 11.9 milliamps, which is 0.0119. 220. Right, so our R2 value is actually 220 ohms. That's what we expect R2 to be. It's 220 ohms. And at this point, you can find your total resistance and you can double check all your other values if you wanted to kind of cross check that. That is what we want. Questions?